In our previous video, we talked about homogeneous and heterogeneous catalysts. But did you know that nature also makes catalysts? Whenever you have a natural catalyst that is also a protein, that type of catalyst is called an enzyme. Enzymes work by allowing a substrate, which is a biologist's word for a reactant, to come into a special location on it called an active site. Active sites are almost always custom shaped to fit their specific substrates and no others. We call this ability of an enzyme to be custom fit to its particular substrate its specificity. In this diagram, we can see an enzyme whose physical shape is represented by all these purple blobs, where it is not interacting with a reactant or substrate. When it comes closer in to a substrate, the substrate docks in its active site. An enzyme specificity, then, is the result of it having a very specific, custom-tailored shape to fit the specific reactant or substrate that the enzyme binds to. When an enzyme and a substrate are bound together, we call the resulting molecule, enzyme and substrate together, the enzyme-substrate complex. Once an enzyme has bound its substrate into its active site, it then catalyzes its particular reactant to convert that substrate into a new product or products and then releases them. The idea that an enzyme is custom shaped to fit, transform, and then release its particular substrates is called the lock and key model. This property of enzyme is what causes them to have such high specificity. This cute depiction shows us a simplified version of the lock and key model. We can imagine, for instance, an enzyme having a specific shape that is perfectly tailored to its substrate. The substrate comes in, binds to that enzyme's active site, and then the enzyme begins catalyzing a conversion of that substrate into products. Once that conversion is complete, the products now have a different shape and are released back into the environment. This is the lock and key model. I'd now like to take a very cool quote directly from our text. It says, "Enzymes are enormously more efficient than non-biochemical catalysts. The number of individual catalyzed reaction events occurring at a particular active site, called its turnover number, is generally in the range of 103 to 107 per second, which parenthetically is much, much higher than most human-made catalysts. Such large turnover numbers correspond to very low activation energies. When compared with a simple chemical catalyst, then, enzymes can increase the rate constant for a given reaction by a millionfold or more." Simply stated, in the immortal words of a biochemistry professor that I once had named Dr. Steve Ost, nature is the greatest chemist. This takes us to a wonderful lecture question. The primary source of the specificity of enzymes is what? I'll let you read these options and answer it on your own. I'd like to conclude this video by reading a specific section on nitrogen fixation directly from our text, just because I think it's super cool. It says, "Nitrogen is one of the most essential elements in living organisms, found in many compounds vital to life, including proteins, nucleic acids, vitamins, and hormones. Nitrogen is continually cycling through the biosphere in various forms, as shown in figure 14.23. For example, certain microorganisms convert the nitrogen in animal waste and dead plants and animals into N2 gas, which then returns to the atmosphere. For the food chain to be sustained, there must be a means of converting atmospheric N2 into a form plants can use." I'm going to pause and just mention, N2 is a form of nitrogen that the vast majority of organisms on this earth cannot do anything with. Yet all organisms on earth have to have nitrogen to survive. So how in the world do we do that? Well, we'll read on. "For this reason, if a chemist were asked to name the most important chemical reaction in the world, she might easily say nitrogen fixation, the process by which atmospheric N2 is converted into compounds suitable for plant use. In other words, useful forms of nitrogen. Some fixed nitrogen results from the action of lightning on the atmosphere, and some is produced industrially using a process that we'll discuss in Chapter 15. About 60% of fixed nitrogen, however, is a consequence of the action of a remarkable and complex enzyme, nitrogenase. This enzyme is not present in humans or other animals. Rather, it is found in bacteria that live in the root nodules of certain plants, such as the legumes clover and alfalfa. Nitrogenase, this glorious enzyme, converts N2 into NH3, a process that, in the absence of a catalyst, has a very large activation energy. I'll pause here because I've probably said enough. The bottom line is this. Without the nitrogenase enzyme, the biosphere's ability to convert N2, which is a virtually useless form of nitrogen, into NH3, which is a useful form of nitrogen, would not exist, and therefore life on this planet would not exist. I am very grateful that we have enzymes in nature. This takes us to the end of this lecture and the end of this chapter. Please stay tuned for our next chapter in which I'll teach you something about something that has to do something with chemistry. Until then, have an enjoyable rest of your day.